Okay. Now, this is the CLO that we have to start. And the statement for the CLO is discuss the importance and usability of dynamic programming strategy in solving problems. So this CLO is about dynamic programming. And we will study some different topics related to it. For example, longest common subsequence, matrix, chain multiplication, and then shortest pass. So we will go with these three ones, and there can be some more topics also in this category, but we will go with these 2, 3 topics, huh? But before that, what is dynamic programming? So in dynamic programming, the first thing is that when problem is given to us, then in with this dynamic programming approach, we will divide that problem into subproblems. And then for those subproblems, we will find the solutions. And then we will put all those solutions together to get a final complete solution for the main problem. So this is the definition for the dynamic programming. So we will divide the problem into subproblems. And then for those subproblems, we will find the solutions. And then we will put them together to build or to form a complete solution. Okay. First, we have some theoretical things like importance of DP, where we can apply them, what are the limitations of DP, when to use DP, okay, what would be the situations that after identifying that situation, you can say that now we can, this is the position, this is the situation where we have to use the DP, what are those? And then we are starting it properly with the algorithms. But before that, what is the importance of this DP? First thing is efficiency. See, if you will build some algorithm using this DP approach, then you will reduce the complexity of the problem from exponential to polynomial. Exponential is higher complexity or polynomial is lower. So I can get into further details, but mostly people have the understanding of this. So here k raised power n, k means constant and n is the size of the input. And here polynomial means n is the size of the input and k is constant. And then you can understand if 2 raised power n or n raised power 2, then which one is higher, you can understand. Huh? So the first thing of this DP is that it reduces the complexity from exponential to polynomial. The second importance is that it gives us a optimal solution. So this approach gives us or guarantees an optimal solution to any problem. Why? Because in DP, it finds optimal solutions for the subproblems. And for those subproblems, all the optimal solution, or you can say suboptimal solutions for the subproblems. And then it will collect them and it will give you finally the optimal solution. So in DP, even for the subproblems, when you have divided your problem into subproblems, even for those subproblems, it will give you optimal solution. And then you will combine all those optimal solutions to get the optimal solution for the major problem. Avoid redundant calculations. In this DP, when we are calculating solutions for the subproblems, we are storing them in some kind of an array. And if that subproblem is coming again, We are not calculating that subproblem again. We are using the result which is already calculated and stored in the array. And in this way, we are ignoring the repeated subproblems. Okay. You can also call them, we are ignoring redundant states or redundant calculations. You are avoiding them, you are ignoring them. And then clear structure. In DP, there is a recursive, okay, approach. There is also a iterative approach, but there is a recursive approach through recursion. So, and when you have a recursive approach here, then your code normally becomes shorter. Okay, you know that, huh? Otherwise, you have to write for loops and the body of the loops, etc., etc. But when you have the recursion is also behaving like iteration, but it is with the call of the function. So when you have recursion and a recursive nature in your program, and with this recursive nature, you will handle different subproblems through this recursive nature. Huh? Actually, you will divide your problem into subproblem, or when you will call the main problem, it will be divided into subproblems, for example, two recursive calls, and then it will be further divided. It will be further divided like that. So there would be a relationship between the subproblems. So this recursive nature and this relationship between the subproblems, it will normally provide a clear structure uh, for modeling and designing algorithms for your problems or for solving problems. These are some important points where we can apply or where we are using these algorithms. So mostly we use this DP for optimization and combinatorial problems. Optimization means those problems where you want to find an optimal solution always. Combinatorial problems are those in which you have to calculate some all possible combinations, huh? Like all possible permutations. If you have studied discrete math, then I'm sure that you have studied combinations and permutations there. So mainly we use this algorithm for this purpose. And for example, there is an application that is called longest common subsequence, in which we are finding the longest sequence which is common between the two given strings or sequences are. You will give two strings, and this algorithm will find the longest common subsequence between those strings. So that is called LCS. So this is also, we will study this, and this is also an application of that algorithm. Matrix chain multiplication. This is a problem of matrices multiplication. You have more than one matrices and you have to multiply them, huh? But for that, this algorithm will do what? It will identify or it will determine the best possible parenthesizing. It will identify the order by putting parentheses around it, that I will multiply. For example, if these are matrices, it will multiply by putting parentheses after it, that I will multiply these two parentheses first, and then whatever the result is, I will do that with that. So it will determine the optimal parenthesizing. What is the best optimal parenthesizing through which you will get that you will get the minimum number of multiplications for those matrices. If you want to multiply those all matrices, what is the minimum number of multiplications needed to multiply all those matrices? This algorithm will find that. We'll find that number along with that parenthesizing order. Okay, just wait and then wait for this azan and then we will start it again. Okay. Uh, Now, the third topic that we will cover in this CLO is shortest path algorithms, where you have to find the shortest path between the nodes, you can say between the between all pair of vertices, all possible pairs of vertices in a graph, and then you have to find the shortest path for the between them. And for that, for example, we have a algorithm that is called Floyd Warshall algorithm for this purpose, for finding the shortest path. And this is the algorithm name. It is written here. So we will also do that. Um, and there are some other applications, or there are some other algorithms which can use dynamic programming. Dynamic programming is a technique. Okay, it is design strategy. It is a what? It is a design strategy for, and you can apply for any problem which will have these attributes. By identifying those attributes first, you can apply then these approach for those algorithms for those problems, and you can build your algorithms. For example, knapsack problem. What is this? You have a knapsack called backpack. So in that knapsack, you have to put some items in it, and those items have the value. But how you have to put that? Maximizing the value of items. placed in the knapsack. So you have to put these items in the knapsack in such a way that you will get the maximum value, maximum profit for those items, huh? Without exceeding its weight capacity. That knapsack, that bag has some capacity. So you don't have to exceed that capacity. And then you have to put also the maximum, sometime maximum number of items with maximum profit, huh? And sometimes any number of items with maximum profit. So this is that problem. And then coin change problem, what it is, here some amount will be given to you, and then you have to provide the change for that amount in coins, coins. I'm not going into detail. Some specific coins will be given to you, okay? That is that problem. So these highlighted ones, we will cover these three highlighted one. We will also cover this, but in some other CLOs, okay? You will know that what is NAPSOP, what is coin change or whatever, okay? But in some other CLOs. Now, what is the limitations of DP? What are the issues in DP, okay? Before that, you only have seen maybe the positive thing, but now we are on the negative side. What is the issues of DP? The first issue is that it is this DP you can apply only to those problems which will have the optimal substructure and the overlapping subproblem properties in it. These are the two properties. These are the properties of dynamic programming. One is called optimal substructure. You will see what it is, you will see later on. One is called optimal structure, other is called overlapping subproblem. If the problem has these two things in it, only then you can apply DP, otherwise not. This is also a limitation, huh? Limit, not beyond that. High memory usage. When we are storing the solutions for the subproblems into an array, well, there can be many, and you are using some that array, you can call it array, you can call it table or anything, huh? And normally for these problems, you will see that there is too much calculations that you have to do. There are too many sub problems that can exist for a problem, and you have to store the solution for that. And then if you are storing the solutions for that, then you are using high memory. Complexity of formulation. Complexity of formulation means complexity of designing, building, huh? Form. Because the recursion is involved in it, recursion normally makes the structure of the program easy, but difficult in understanding. Okay. If you will try to understand some algorithm in which loops are used, for example, binary search with looping, then you will understand that algorithm. And then you have another program of binary search with recursion. So if you will read the program with looping, you will understand it easily as compared to recursion, okay? Because in recursion, you have to memorize which call is executed, which call is still in process, etc., etc. So the recursion is complex. So, so when you have and for recursion, you have to build a recurrence relation. Recurrence relation, you have to build that. That would be the equation, huh? That would be the equation that will calculate the current values from the previous values. So identifying or building this recurrence relation and identifying different states which are involved in your problem, you have to represent different states, nodes, or whatever. So, and their designing is what? It is difficult. It is what? Difficult. It is complex. So if you have to build some algorithm for some problem using DP, then it is not easy, okay? Then it is not easy. Then its formulation can be complex. And next is, it is not always give you efficient solution. Huh? Sometime for some problems, if you will use other simple algorithms like greedy or divide and conquer, which is simple. For some problems, you can use DP, but if you will use greedy or divide and conquer algorithm, which are the easiest one, then sometime it can give these easy algorithms, it will give them good solution as compared to DP, okay? As compared to DP. It will give you fast solutions as compared to DP, okay? Now, now the question is when to use uh, dynamic programming. What are the situations when we have to use DP? Those situation is when your problem will have these two things, then this is the situation that where you can use the dynamic programming. So what are those two things? So in short, in other way, when we, if this is the question, when we have to use DP, the answer is if you will have these two things available in your problem, only then you can use the DP. And what are those things? Number one, optimal structure, overlapping substructure. Now, I need your attention because this is the point. If you will understand these two things, then you can understand that this is something related to DP, this is something related to something else. Optimal substructure. Substructure. It is related with the structure. If you can divide your problem into sub problems, if somebody has given you some problem, and then if you are looking which approach I have to use, DP or divided conquer, greedy or what, and first you can see if you can divide that problem into sub problems, and then you will find the solutions for those sub problems, and those sub problems will contribute their solution for the final solution of the main problem. If this property is existing there, then this is called optimal substructure. In short, just in short, if you can divide the problem into sub problems, then this is called optimal substructure. The complete definition I already told you. Can divide your problem into sub problems, then you have to find solutions for those sub problems, and then you have to put them together to get the major, to get the solution for the main problem. If you have this thing in your problem, then you can go on with. But this is called optimal substructure. Okay, this is with the structure. One thing divided into that thing. This is with the structure. Now, overlapping subproblem. Overlapping subproblem is when you have repeated problems, when you have repeated subproblems in your problem. How you can identify that overlapping this overlapping subproblem you can is available in the problem? How you can identify? If the subproblems, if you have repeated subproblems in your problem. For example, you have calculated something already, and then you are calculating it again in some. You are calculating it again somewhere. Then this is some example of that repeated process. So when the problem has these repeated subproblems, and these repeated subproblems, or you can say when one subproblem is becoming the part of another problem. How? For example, if you are calculating this, this is the first call to the function, and then this is f of n. F is a function. For example, f of n. I have this example here. Here we are calling f5 here, and then this method in its body, it is calling again with f of n minus 1 and f of n minus 2. This is divided into subproblems, and it is further divided into further problems. And here we are saying when one subproblem is part of the solution to another subproblem. Here if you will see, for F5 we are calling this, for S6 we are calling this, and this F4 is existing here and also existing here. This F4 is a part of the solution, or you can say these two are part, giving a solution to this one, giving a solution to this one. But anyhow, this F4 is a part of the solution. And here now, overlapping, when one subproblem is part of the solution to the another problem. Or in short, you can say when you have repeated subproblem, then that state will be there. Okay. Then this, whatever is written here, when you have repeated subproblems, then this condition would be there. Okay. Anyhow, moving next. Now, two properties. You have to identify two properties in the problem. Optimal substructure, which means you can divide the problem into subproblems. And the other additional things, okay, don't say, but keep it in your mind, huh? That subproblems, you will have the solution, put them together to find that. And then overlapping subproblems, what? It means what? Repeated subproblems. But in these repeated, this will become the part of the solution to the other. Huh? Keep that definition in your mind. Huh? But shortly repeated subproblems. So these are the two things. If you will have these two things in your problem, you can use the dynamic programming approach. You can use the dynamic programming approach. How? Now we have seen the definitions here, but how we can identify these two things practically. Huh? So first we are checking overlapping subproblems with example, and then here we are checking optimal substructure with example to understand these two concepts further. For example, here we are taking an example of Fibonacci numbers. What is Fibonacci numbers? These are Fibonacci numbers. Starting two numbers are 0 and 1, and then we are adding them, and we are getting the next one. And then we are adding these previous two, and we are getting the next one. We are adding these previous two, and we are getting the next one. We are adding these previous two, and we are getting the next one. We are adding these previous two, and we are getting the next one, and so on. This is called a Fibonacci series or Fibonacci sequence. So in the Fibonacci numbers, okay, this series is starting with 0 and 1. The first two numbers will be given to you. And the next numbers are created by adding previous two numbers. And the first 8 numbers for this series is this. Now, we are trying to understand overlapping subproblems. Overlapping subproblem means repeated subproblems. Repeated. I have changed the order. Huh? Repeated subproblems. So here you can see f of 5 and f of 6. They are calling f of 4 and f of 3 from in the tree. And this f of 6 is not available, but anyhow, f of 6 will use what? F of 5 and f of 4. Because in the Fibonacci series, we are using previous two. So I am using that concept, previous two. For if you are going to calculate number 6, then you need previous two numbers, f of 5 and f of 4. And for f5, f of 3 and f of 4. And if this is the tree, for that f5, we are calling something here f5, which is, it needs for fifth number of Fibonacci, it needs 4 and 3. For 4, it needs 3 and 2. For 3, it needs 2 and 1. For 2, it needs f1 and f0. Huh? And then how it will go? Fibonacci numbers 1 plus 0, it will 1 plus 0, it will give you 1. And here f of 1, it will give you 1, no? Because it is the first number. Huh? 0 and 1 is given. So f1 will give me 1. So 1 plus 1, it will give me 2. And here 1 plus 0, it will give me 1. And then 2 plus 1, it will give me 3. Huh? And then here 0 plus 1, it will give me 1. And f1 is already 1. So 1 plus 1 is 2. And then 3 plus 2 is 5. So now you can see 5 here. Here you can see the number 5, 3, 2, 1, and then 0. Okay. So 5, 3, 2, 1. And these first two numbers are given. Huh? Just for a logic of a program. So that's why I said, otherwise it is not necessary to understand what is written here. You only have to understand this. F4 here in this series, F4. What is the number 4? This is 0, this is 1, this is 2, this is 3, and this is 4. That is written here 3, F4. And f of 3 is what? From here, it is 2. So 3 plus 2, when you do add it, it will give you 5. Similarly here. But here, when we are calculating this F5 and X6, so for example, for sixth Fibonacci number, that sixth Fibonacci number is a combination of what? It is a combination of 5 and 4. And it is giving 8 is equal to 5 plus 3, like that. And this, using previous two numbers, is true for all the Fibonacci numbers, except the first two. For all these numbers, how you are getting these numbers? By adding previous two. This is true for all the Fibonacci numbers. Now, we are still not talking about the overlapping problem. Let's see that here in this blue part. So if I will write something for S6 and if I will write something for F5 by using the same logic, then I can see that this F4 is available in both the cases. And overlapping is something like that. For example, what is overlapping? If you have this set and that set, then this area is the overlapped area for these two sets, And then you can say these two sets are overlapping. And for us, F5 and F6, they are overlapping. If it is F5 and if it is F6, they are overlapping by this common area, F4 and F4, okay? These are repeated subproblems. And if you will even see in this tree, for example, here with different colors, this F1 is here, first time it is here, then it is called a here, calling here. So how the F1 is repeated many times in this simple tree. Similarly, F0 is repeated 3 times. Similarly, F2. Similarly, F3. So most of the nodes are repeated, huh? In this small tree. So you have to identify this property that this is called overlapping, huh? And now by you have shown that what is overlapping subproblem means by these examples. You have shown it here. Huh? For F5 and F6, F4 is the common subproblem. And we can see many different cases in the figure. So this is the property of what? Overlapping. This is called overlapping subproblem. Now, for the same example of Fibonacci, we know that we can calculate the nth number in this problem by using previous two terms, n-1 and n-2. By using previous two terms. When we will add them, we will get this next one. And this is true for all the Fibonacci numbers, except the first two. We already said this statement in previous discussion. When you are getting numbers, next numbers from previous two, and every number you can get from the previous two, which it means that every number is divided into parts. Huh? Another other meaning is, for example, if I say I can get the number n through n minus 1 and n minus 1 subproblems, I can get. And it is true for all the numbers except of the first two. What it means? It means that I can divide the nth number into previous two numbers, or I can get it from the previous two numbers, which means problem is divided into subproblems. Generally, how you can say that? It means that problem is divided into subproblems. And this is the property of optimal substructure. And this is the property of optimal substructure. For this problem, you can say, and it will give you some tree, okay, like that. So now we have seen that what is overlapping and what is overlapping subproblem and what is optimal substructure. And now we are a little bit ready to apply the DP concept on some problem. So, but before applying that, we will try to understand that there are two approaches in it. First, we saw that when we can apply the DP, then I told you that if you have the overlapping subproblem of the optimal substructure property in it, then you can use. But now, okay, you have some problem in which you have those properties. Then there are two design strategies for DP. Two design strategies. Or you can say two approaches of DP. I think two design strategies is a better word for it because it will give you more understanding. Two design strategies. One design strategy is top down. And the other name for this top down approach is memoization. In this approach, you will start solving the problem from the last number. If your if your array has 10 elements and n elements, you will start calling your problem with the n. And that problem, you will get it from the previous two numbers. So 9 minus 8 from right to left. It is written right to left. Okay, don't worry. Okay. So n minus 1 and n minus 2, and you are getting n. And then that 8 you are getting from n minus 1 and n minus 2, 7 and 6, and that. And in this way, you are going to call each subproblem until you reached at the leaf nodes. And you can solve this problem by recursion only. You can solve this problem by recursion only. This is called top-down approach. And the other name for it is memoization, because we will use some array in this approach, which is called memo. And that memo will store the solutions of each and every subproblem that is existed in your problem. That memo would be an array that will store the solutions for each subproblems. Now, if you will read, then you will understand. Okay, recursive approach with memoization array. So, okay, recursive approach, which means we will use recursion. And we will use memoization array. Why we will use it? To avoid computation of the same problem again. In this memo array, we will store the solutions of the subproblems. And if that subsolution is coming again, then we are not computing it again. We are using the solution which is available in that memo array. We are using that. Okay, that is what it means. And now, before any recursive call in the program, in the algorithm, before any recursive call, before something calling recursively, we will check that if the memoization array has already the solution for it, we will use it. And if that is not available there, only then we will go for the recursive call to find the solution for that subproblem. Here it means, again, before any recursive call to any sub problem. Okay, this is what sub problem is not mentioned here, so then it can be ambiguous, but I am giving that word to you. Before a call, before a recursive call to any sub problem, we will first check that the solution for that sub problem is available in that memory. If it is available there, we will use it, and we will not call recursive. If it is not available there, then we will go for recursive call. It will save our time, because then you will not compute the sub problem. You will use only the answer which is available there. When the recursive call is over, okay, then we store the solution in the memory. When you will call the recursive call, in that recursive call, you will execute that function. And in that function, this statement would be there that you will calculate the solution and then you will store it into the memory. Anyhow, you will see this is something theoretically. This is something theoretical. So one design strategy is top-down approach. The other name for it is memoization. So you can say dynamic programming via memoization, dynamic programming via top-down approach. We can use the words like that. Other one is bottom-up approach. And here in this approach, we are using also again an array, and the name of that array mostly would be table or DP or something like that, but not memo. Okay, memo is something fixed for, not fixed. You can use other name, but most of the literature you will see memo there with the recursion. And here in this approach, bottom up means you are going from the bottom of the tree, to up towards root. And here, if this is the tree, on the tree, this is n, and then the numbers are reducing up to 0. Huh? And here, bottom up, you will start from 0 and then you will go up. So we will start with the smallest subproblem that can be starting initial subproblem. Like for Fibonacci series, it would be 0 and 1. Huh? And then gradually, we will build up an iterative solution. Here, we will not use recursion. In the previous top-down, we will use recursion. And here, we will use not recursion. It is iterative design. We will use loops. Okay. We will gradually build a iterative solution in bottom-up direction, from bottom to up, like that. For example, here, you are calling your function f of n with n is equal to 10 initially. But then when you called first, you are calling your program, like then it is going here. It is starting from your initial state, then putting that result into your next state, gradually, and finally it will give you the answer here for f of 10. Okay. So you are giving n is equal to 10, but then it is using a loop which is starting from 0 to 10. And then it will give you the answer. Huh? So it is a tree, but it is straight linear tree going. These are the simple calls. Okay, I already explained that it will use a table, and that table would be an array. In this table, why we will use it? For the same purpose like memo, huh? For storing the solutions of the subproblems. So we will fill this table, which is an array, with the solutions for the base cases. For Fibonacci numbers, for example, it can be 0 and 1. Huh? For the base cases, we will store them. And then the remaining entries of the table, which means remaining solutions for the other subproblems, we will calculate, and then we will fill it in this table gradually. These are the two design strategies. One is top-down, other name is memoization. And in that, you have recursion and the memory. This is bottom-up. You will start from the initial values up to the last values. And here you will use a table that is also an array, and it is iterative design. It is not a recursive design. Uh, Before starting some uh, actual example of DP, which is from here, I am also introducing another topic into it. This is not a big topic, so that's why it is just. Uh, I can remove it. Okay, I can remove it. This is not necessary now. But when I was teaching in the previous semester, I was teaching algorithm and complexity and design analysis. There were two different courses. And there is a minor difference between the CLOs. So due to that reason, it is like that. This brute force and exhaustive was existing in the other course. But it is the topic of algorithm, so you can also take it. Brute force and exhaustive approach. What is the difference between these two? They are almost similar with a minor difference. With a minor difference. You know that if brute force means checking all possible combinations, huh? Checking all possible combinations to find a solution for some problem is brute force. And the answer is also not guaranteed that it would be optimal. Shortly. And the answer that you will get is also not guaranteed that it would be optimal, no. And then you are checking all possible combinations. And this approach would be straightforward and simple. You can go on with any order. But exhaustive search is what? It is systematic. You will build some nizam. It is systematic. And the solution that you will get through this, you will again check all possible combination, but with some mechanism, with some advanced mechanism than brute force. And the solution that you will get for this exhaustive approach, that would be optimal. That is also the difference from the brute force. That is also the difference from the brute force. So now if you will read it quickly, then everything is okay for you. Brute force. What is brute force? A straightforward, which means simple, unsophisticated. Huh? Unsophisticated approach, which means unordered. Huh? That is unordered approach that tests every possible combination to find a solution without the guarantee of optimality. And what is the example for this? Linear search. If you have an array of 5 elements and you have to find element in it, you have to compare one by one. You have to check all the combinations. And then you can give the solution. This is a simple example, so that's why. So searching for a specific value in a collection or in an array by checking each element one by one, this is an approach of brute force. This is brute force example. Exhaustive search. This is systematic approach, which means a little bit advanced than the brute force. A little bit organized. Okay, now it is organized. Huh? And here again, you will check all combinations. You will check all combinations and permutations of that problems. When we say combinatorial problems, it means something you have to calculate, see all possible combinations or permutations. So, so this is something an organized approach to these combination problems where you will evaluate all possible candidate solutions to find the optimal ones. This is also the difference. It will give you optimal solution if more than one solutions are available for something. What are the examples? Traveling salesman problem. No, you know that TSP is a bigger problem than linear search. And in the TSP, so the salesman have to visit each city for only once, huh? And the objective is that the salesman want to visit each city, and he can visit all the cities only for one time, and then he will start his journey from one node, and he will come back to that node again. So by considering these three, four constraints or conditions, you have to provide the solution. That is the solution. That is the traveling salesman person problem. And you have to find the shortest path. Huh? This is also an objective. So this problem lies in the category of exhaustive search. Now there is one example for this brute force and exhaustive approach. Take this, and after that we will come back to our DP topic. You will also get an idea of DP also with this example. Now, example 1. What is the question? Consider the problem of finding the Fibonacci sequence. We are still with that same problem, okay, so that you will not feel difficulty. So consider the problem of that Fibonacci sequence. And what is that? Initial two numbers are given, and then the next numbers you are getting after adding previous two. This formula, we know that. So then for this problem, the question is design an algorithm by using brute force or exhaustive approach for this problem. And that algorithm is here. And here in this algorithm, that is not an algorithm, that is a program, Python code actually. If you will remove this, then the remaining will become the algorithm, okay? Because now the program syntax of the programming languages has become so easy and so close to your natural language like Python, that now you can say the code of your Python as like an algorithm, huh? But for that you only have to remove this main from it. Otherwise, if you will not remove, that is also okay. Anyhow, here, if this underscore name main, which is the main method, and here n is equal to 5, and print, we are using print, and then fib into n. Fib is the name of the function, and when you have the parenthesis, it is giving you an idea that it is a function, and you are passing n into it. So this fib, you are calling this function with the value 5, with the value 5. And here we are checking if this n is less than or equal to 1, no. If n is equal to 1 or 0, 1 equal to 1, 0 less than 1, this condition would be true, and you are returning that n, okay? So for 0 and 1, you are returning that these numbers from here. This is called the base case. And if this condition is false, for example, n is 5, then this n 5 less than or equal to 1 condition false, and you are coming here. And then you are calling fib 5 minus 1, which means 4, plus fib 5 minus 2, which is 3. For this fib, we are calling fib 5, and then we have a call f4 and f3. Understood? So tree is an exact understanding of recursion. For at any time, for some time, if you want to understand recursion, draw a tree against it, and then you will understand. And now we know that until these calls will be finished, we are not going out of it, okay? So then what? F of 4, we are calling this function with 4. And this is remaining. F of 3 is remaining. And then we have to add values, huh? So now fib f of 4. Okay, when you call with f of 4, 4 less than or equal to 1, condition false. And then you are calling this fib 4 minus 1, 3. And 4 minus 2, 2. You are calling, these are the further two calls. For it. And this call is still pending. This call is still pending, huh? But we are going with the default order, huh? And then so this is still pending. Okay, how I can say, okay. with complete circle. And this is complete circle. This is now done. And then f of 3, you are calling again with fib with value 3. And this 3 less than equal to 1, condition false, and then you are here. 3 minus 1, 2, and 3 minus 2, 1. So with 3, you have these calls. And this is pending. When you have these calls, now you are calling fib with this f of 2. When n is equal to 2 less than equal to 1, condition false, and then you are here. 2 minus 1, 1, 2 minus 2, 0. And then you have these two calls. Huh? Now when you are calling this, f of 1, now when you are calling this fib f of 1, n is equal to 1, and here you are checking 1 less than equal to 1, it is equal. 1 equal 1. So n, if it is 1, it is returning what? It is returning n. It is return, and what is the value of n? 1. So it is returning me 1 here. And then, okay, now here, if I will remove some uh, of the drawings, if I will remove, so that I can write something here. Okay. Now, this f of 1, you know that we are getting 1 here, and then this plus here, and then this fab, which means this 0, 1, huh? And then when f0, you will call it, and when n is equal to 0, then 0 less than or equal to 1. Yes, it is less. 0 is less than 1. Condition true. And then it will return 0. And then you will get 0 here. Huh? So you are getting, for f0, you are getting 0. And then plus is between them. So 1 plus 0, you will get, and that 1 plus 0, it will be added, and it would be returned. Return to what? Return to previous call. And when it is f1 and f0, this is 2. When you called n is equal to 2, it is 2 minus 1, 1, and 2 minus 2, 0. These are then calls. And at that time, n was 2. Huh? So then this 1 plus 0, you will get 1 here. Understood? And for f of 1, I know that for f of 1, what I will get, I already calculated for f of 1. If this solution I already stored, I will store it in a memo, but here I'm not storing it in memo. It is brute force. Huh? It is brute force. Huh? So brute force and exhaustive. So here I am computing each repeated subproblem again and again because the topic is different from the DP. Huh? But in DP, I will use memo here for repeated sets, and I will not call it again. I will use the solution. Huh? But here, brute force and exhaustive, so I have to compute each and every sub solutions again and again. So then for f of 1, okay, I will go again with 1. And for f of 1, I will get, I know the answer is what? 1, because it will return 1. And this is the call against this. And then plus between them, 1 plus 1, you will get 2 here. And here plus 1, you will get 1 here, 0 from here. Due to this plus, you will get 1 here with this call. And then 2 plus 1, you will get 3 here for this f, so f4. And here 1 plus 0 with plus, you will get 1 here. And f1 will give me 1, and then plus, it will give you 2 here. And then this 3 plus 2, you will get 5 here. As a, this will be returned finally from this program. The output of this program would be 5. Understood? And here you have, I don't know either I have explained it well or not, but here each and every, you will have each and every call, okay, like that. And that each call is represented in this tree, okay. Now, what is now the question is what is the time complexity of this algorithm? Time complexity, time. Maybe in the previous practices, I told you time complexity. Okay, here this is constant, huh? This is constant, this is constant, this is constant, this is constant. But we have a recursion here, okay? And recursion is also like a loop, huh? So now we have to understand that how this recursion is going, how much time, huh? Otherwise, rest of the statements are constants. But here we have to identify that how much time this recursion is going on. And the easy way to do that is you have to see that how many calls you have for recursion. So the function fib, and we are calling fib here, one call, another this call, and we are adding them. So there are two calls on each. On each recursive call, this is a recursive call, and in this we are calling two times. Huh? So this is 1 plus 1. Due to this plus, it is 2. Huh? So two calls, two recursive calls. Okay, now we know that two recursive calls. But how many times maximum we are going? If you will look on this simple tree, which is for n is equal to 5, then you can say, okay, if n is equal to 5, then 4, then 3, then 2, then 1. And even then one time more for 0, but it's not an issue. So maximum depth is what? N time. Maximum number. And then and then what? So I can say it when I say 2 raised power n times 2 raised power 10, 2 raised power, for example, this one, okay, it will give me what? 2 raised power 6, 1, 0, 1, 2, 3, 4, and one more time. Huh? So then you can count this. So that what would be the number of calls at the last depth level, at the last depth level. So anyhow, this depth is giving you that idea. So so then you can write that if your n is 5, then that you can write 2 raised power 5 or 2 raised power n. If you want to represent it in general terms, then you can write it n. So, and what is this 2 raised power n? If you will write it in a big O, what it means? This is what? K raised power n. This is k raised power n. What is this type? I said somewhere, I don't know. K exponential, okay? This is exponential complexity. If somebody will write, so then he is writing. Okay, otherwise the answer is this. What is the complexity of this algorithm? Time complexity? Order of 2 raised power n. Why? I explained it to you. Two calls, two recursive calls, two, and it is executing n times. So due to that reason, it is in between. Huh? Due to that reason, it is 2 raised power n. Okay. Now coming back to our DP topic. How DP will work? Brute force is now clear. Huh? How will DP work? So here for this problem, for this tree, now we know this tree. And here we saw that these different colors, which means these are the overlapping problems. Huh? Overlapping means repeated. And all these colors have repeated. And if we will use some memo array here, and if we will use whatever the solution of this sub problem is, if we will store it in the memo, and next time when it is called, we will use the solution answer directly from here rather than computing it again, then we will save the time. Then we will save the time. So here overlapping problem is causing huge exponential computation. And if we will remove this overlapping, if we will handle this overlapping, then the time complexity of brute force approach will be reduced from this exponential to linear. This is called a linear order of n, linear complexity, which is the complexity of the linear search, order of n. So this is 2 raised power n, but this is only n. 5 elements, 5 operations. 10 elements, 10 operations. And here 5 elements, 2 raised power 5 is 32, maybe 32 operations. So we can reduce this order of 2 raised power n by 2 order of n by using memoization and recursion. Okay, now this is not needed, but anyhow, theoretically, how it will work, how the DP will work. Okay, this is written something according to the steps of the algorithm. How the first step, how the second step, how the third step. The first step that you have to do, how will DP work? Here we are still how it will work. So we have to identify overlapping problems as we have seen it here in the previous, and we know the complexity of it. We can reduce it to order of n by using what? By using memo array and the recursive approach. That is the first category design strategy of the DP. What we have to do? We have to identify the subproblem. Identify subproblem means the problem can be divided into smaller problems. So divide the main problem into smaller independent subproblems. Like for f of n, we have f of n minus 1 or f of n minus 2 for Fibonacci. Store solutions. So then we have to solve each subproblem. We have to store the solution in the memo or table. Both are arrays. Memo is for the first strategy. Table is for the second design strategy. Both are arrays. Both are arrays. Memo is what? For top down. Table is for what? Bottom up. So you have to store the solution in these arrays, and then you can use this solution in future. Why? Because we don't want to recompute them again. Then build up the solution. So we have stored solution in the memo. So we will use the stored solution in the memo, and also for new subproblems, we will calculate the result of for them. And after calculating, we will store them in also memo. Okay. So every subproblem which you will visit one, you will calculate the solution and you will store it in the memo. And if it is coming again, you are not computing it. You are using the stored result. So you will build the solution to the main problem by using the stored solution. For example, for f of n, you will use f of n minus 1 and n minus 2. And these n minus 2, if they are available in the memo or table, you will use them from there. If not, you will calculate them and then store them. Anyhow, for this Fibonacci, you will use the solutions from the table, and then you will add them, and then you will give this to f of n. And this is just for previous example. Now, take this only, and then I will stop maybe, and we will start it from here. Let's see what using. Now this is dynamic programming using memoization approach. Using what? Memo. Memoization approach means here in this program, we will use some array that is called memo. And here, whatever the algorithm we have here is, the running time of that algorithm is order of n, and the space it is taking is order of n. That is same Fibonacci that you saw in the previous brute force approach with complexity order of 2 raised power n. Now, with this memoization, running time is reduced to order of n. And space is also reduced to order of n. Now, the question is, I can give you that brute force algorithm in the exam. And I can say that the complexity of this algorithm is order of 2 raised power n. Now design a algorithm using dynamic programming, which can reduce the complexity of this given algorithm to order of n. Okay, now you have to keep that kind of understanding. Okay, you don't have to go with describe this and define this. Okay, you have to keep this kind of understanding on your mind. Why these slides are connected with each other. Okay, why each slide are connected with each other. We are going like a article. Huh? So now, okay, look over here. The theoretical things for understanding is written here, which are about steps. The If you want to read, or do it by yourself. Let's see that here. I will read at the end. Here, what is happening here? We have a function that is fib, and we are passing and let it here and start it from here. Huh? N is equal to 5 and print fib n. We are calling some function fib and passing 5 into it, which is this one. Here the 5 will go into it, and then the memo array is equal to -1 multiplied by n plus 1. N is 5, n plus 1 is 6. So -1 multiplied by 6, which means you are initializing this array which had the size 5, all elements with -1. Huh? With all elements, if there is an array, that array is initialized with what? All elements, initial values with -1. Are you understanding what I'm saying? Are you understanding what I'm saying? For example, if this is the array, 3, 4, okay, 5, then initially it is initialized with what? -1, all elements with -1. I'm not able to write it by using mouse pad. Huh? All elements would be -1. Huh? And then return fibrec. Fibrec is this function. And we are passing the n, which is 5, and memo, this array with minus values. Huh? We are passing it to it. Okay, passed. And then base case. If n is less than equal to 1, return n. This is the same as you saw here. This is the same base case. So if n is 1 or 0, then it would be equal or less, and we are returning it. If n is equal to 5, then we are coming here and then we are checking memo into 5. Memo into 5 not equal to 5. For example, here index is starting from 0, 1, 2, 3, 4, and there is one more 5, and then here it is -1. And then if memo into 5 not equal to -1, memo into 5 is equal to -1, condition false. Here the condition is what? Here the condition is false. That is equal to -1. Okay. So when condition is false, it means solution is not available. Okay. That is what it means. Okay. It means solution for this subproblem, for which we are calling this fabric, it means solution for this problem is not available in the memo because the value of the memo cell is -1. So it means now we have to do a recursive call. So when this condition is false, we are going next here. Then calculate and save output for the future use. We will calculate, we will call the recursive call, and whatever the value we will get, we will again store it into the memo. First, we are checking this memo, and then when we have not found the solution in the memo, we are coming here. And then here, memo into n is equal to fabric n minus 1. If n is 5, then it is 4. And the array, whatever the array is. And then it is 5 minus 2, it is 3. And the array, which is same. Like here, for 5, you have 4 and 3, okay? The tree is like that, okay? The calling tree is like this diagram. So 4, 3 with fabric, and plus is also given here. And this backslash is given for the new line. Huh? That This line and that line is on a same line. Huh? This is Python code, so that's why. Otherwise, you can write it in a simple one line. This plus this. And 4, 3, okay. When you are calling it with 4, okay, then you are calling it with 4 and then with 3. And in this way, this 4 you are called, you will come again. For 3 and 4, when you call again, memo minus 1, and then you will call again. Huh? Memo minus 1, no solution available for the first time. It is coming first time. Huh? And then you will be here for F3, you will call it again. F2, F1, no solution available. You will go to the next call, F1, F1. Now this is decisive. When you will reach here, F1, Fibonacci with 1, and what will happen? So these two will execute first. So what will happen now? So when F is equal to 1, when it is 1, when N is equal to 1, N equal to 1, return 1. Now it is returning. That 1 will be returned. That 1 will be returned. Similarly, for 0, it would be returned. And when, now let's see. This is the call to F2. These two calls are for the F2. Huh? Now let's see. When we called here, this was 1 and this was 0. And 0 plus 1 is equal to that. 0 plus 1, after adding, it will become 1. And that is stored where? Memo into N. What was the call here? F2, 2. What was the value of N here? When the value of N was 2, it was here, the value was 1 and 0. And when it was 1, 0, it is giving us what? 0 plus 1, it is giving us answer 1 after addition. And that 1 will be stored where? Memo into N. N is what? 2. So memo into 2. In the array at this position, we are storing what? 1 now. Updated. This minus 1 will be updated with minus 1. And next time when it will be checked here, memo into 2, not equal to minus 1, not equal to, yes, condition true. And then return memo into 1. Use that value. You are going out of it and you by using that value. If you are feeling difficulty, I can go on the board, okay? If you are feeling on the difficulty. But I am using it also like a board. But anyhow, if you are understanding, that's okay. If you are feeling difficulty, then I can go on to the board. Are you understanding? Don't be shy, okay? Don't be shy. Don't be restrictive. Take it like a home, huh? Consider me like your friend or brother, huh? Don't consider me like your father, huh? Then you will give me respect, huh? Okay. Anyhow, no doubt teachers are spiritual father as per statement of Prophet Muhammad Sallallahu. Teachers are spiritual father. So that status is true for me. But I want to say to you to consider me like your brother so that our environment will be friendly. So if you are not understanding, then I can go on the board. If you are understanding up to now, it's okay, then I can move forward. Now, I can take one more example. Now we understood this part, storing into memo and N, and then we are returning this memo and N. So this part is understood. We understood this part. We understood this part. Everything we understood. But now we can take one more example. Here for f of 3. Yeah? This F2, now we have 0 plus 1, 1 there, which is available in the memo. And F1 is available in the base case. It is like available in the memo. For example, now here. What is the call? F2 is calculated, which is 1. Understood? Now, for F1. And this was the call for when N is equal to 3, for F3. When n is equal to 3 for F3, at that time, F2 was subproblem and F1 was subproblem, huh? For F3. Okay, now take this as an example. When, and we have only this 2 as 1, and then I am removing all these drawings. So this is 0, this is 1, this is 2, this is 3, this is 4, this is 5. And then I said all are -1 except this. Now it has become 1, huh? Now we are going for the f of 3. So this 2 memo into it when n was 2 here, then here it was 1 and it was 0. After adding, we are storing it memo into 2, which n is 2, so here we are stored it 1. And now in the tree, it is with the f of 2. In parallel, in the tree, there is another call which is remaining, f of 1. Huh? These are the two subproblems called under f of 3. Huh? So now our n is 3. Huh? Now, if I'm supposing our n is now 3, if it is 3, then this is the call for the 2 and this is call for the 1, which are the subproblems. So f of 2, when you are calling f of 2, okay, f of 2, n is equal to 2, 2 less than or equal to 1, condition false here. Memo into 2 not equal to -1. Yes, when you will check, it is not equal to -1. When it is not, return memo into 1. For f of 2, it will give you that value. When it is returned, what is that value? 1. So that value would be returned here. And then plus, and then here, this fabric with 1. Okay, you will call it with 1. And then here, n is equal to 1. 1 equal to 1. Yes, return n. It is like a memo. There is no need to call recursive call. It will return 1. When it will return 1, this will be 1 will be here. And this, what? This 1 and this 1. After adding, you will get 2 here. Where you will get 2, but the n is what? 3. So here at 3, you are getting what? 2 for f of 3. And then you are updating it and you are returning it. So at this level, now you have what? Here you have what? 2. And for f1, it will be returned by the base case. That is 1. f0, it will be returned by the base case. And then you will add, it would be the call for the f of 2 and f of 2. But first, here for f2, it will not be calculated. What is the value of f of 2 value is also available in there. You will use that from there directly. And that f2 is available as 1. So then 2 plus 1, you will get 3 here for f4. And similarly for here, what is the value for f of 3? You will get 2 here. Maybe there is no need to calculate further. You can see. But even if it is there, those values are there. Huh? There is no need to calculate this whole tree. There is no need to calculate it because f of 2, when here you will call f of 2, f of t is already calculated. You will use it, the memo. Huh? Again, after this, when it is done, sorry, here. When you will call here for f1, it is already done there. You will use the answer from memo. You will not call this recursive. You will not use this recursive call. And here f of 4, when you will call this with f of 2 recursive call, the solution is already calculated. You will use that solution and then this whole tree is not executed. Similarly here, for f of 3, you have the solution there. Then you will not calculate this. And then how much time? Only this 1, 2, 3, 4, 5, and this 0, 6. Only these. Rest, it is the rest of the subproblem, you don't have the recursive call. You are using memo. Time is reduced. Time is what? Only this end time is remaining, and the rest, this is not needed. Huh? So that is how the time complexity of this is how reduced to, because you are using the solution from this memo. Okay, you are not using recursive call. Where if you will use recursive call, then you can say the complexity is not reduced. But now it is reduced. I have shown you from the tree. And we are using only if n is equal to 5, it is executing 5 or one more time 6. That is n. So that's why it is order of n. Even we have recursive calls here, but due to this memo effect, it running time is order of n. And what is the space for it? It is space complexity are two times of some space complexities. One is physical, other is auxiliary. I already told you. Physical is with the data structure and the algorithm, and data structure and an algorithm, whatever data structure you have. For example, here we are using a memo. A memo is taking n elements. So then it is order of n, space complexity for this algorithm. Only this data structure, and we don't have any other data structure here. Huh? We are using only one array here, memo. Auxiliary is with the runtime. Auxiliary space complexity is when the algorithm will run at that time, what space it will take. And recursion is a mechanism that takes memory at the runtime of the algorithm. When you have the algorithm, and in your algorithm you have the recursion, then you have to build a program for it. And when you will run it, at runtime, this recursion will create a stack in the memory, because recursion uses stacks on machines. And stack is again a data structure. And how much time this recursion is called? We know that it is according to the running time, n time. 5 elements, maximum 6 time. 4 elements, maximum 5 time. And the other, we are not calling recursive in the tree. So auxiliary space complexity for this algorithm is order of n, and the real space complexity is also order of n. Now, if you will read this theory, it is giving you the understanding that how this algorithm is working. Take a memo array initialized to -1. You know that there is a memo array initialized to -1 is here. Make a recursive call. We first check. So make a recursive call means this call that you called here for the first time. Make a recursive call. We first check if the value stored in the memo array -1 or something else. We will first check what is the value in the memo array. If the value in the memory is -1, then it indicates that we have not calculated it yet. We have not calculated the value of it and have to recursively compute it. So then it means we will go there and we will compute it recursively and store it in the memo array as we are storing it here and returning it. So that next time, if the same value is encountered, next time, like for this 2, it was in same value was encountered, then it can be directly used from the memory as we were using this memory directly from the memory. Understood? Understood? This we will do inshallah next. Battery is also red. Okay.